Have you ever been on the floor, everything's running smoothly, and then bam! An alarm pops up on a machine that seems to come out of nowhere. It stops everything, feels completely random, but what if it isn't? Well, today we're going to dive in and pull back the curtain on why these phantom alarms happen, and more importantly, how to stop them for good.
Oh yeah, you know this screen. An alarm history just filled with errors that kill production, drive everyone crazy, and just don't seem to have a simple explanation. But what if the answer isn't some super complex electronic failure? What if it's all down to a simple, fundamental misalignment? That's exactly what we're about to uncover.
All right, so let's zero in on the specific problem here. We're not talking about just any old alarm. We're talking about a very particular set of faults that keep coming back, forcing operators and technicians to basically chase ghosts around the machine. And here are our culprits. Alarms tied to the machine's turret, things like incorrect turret direction or turret needs zero return. They just pop up, you know? One minute the machine is humming along, the next it's dead in the water. This right here is the classic signature of an unstable system. Now, for an alarm like this, what's the first thing you do? You pull up the standard troubleshooting guide. You check the switch, you test the signal, maybe you check the wiring. And look, if it's a hard failure, something's actually broken, that usually works perfectly. But for these intermittent problems, these steps often come up completely empty, and the real root cause stays hidden. So to find the real culprit, we've got to go deeper. Let's get down to the machine level and see how this whole thing is built. We're literally going to dissect the physical interaction between the sensor and its target to understand exactly where the weakness is coming from. Okay, so here are the key players in our little drama. First, you've got the proximity sensor. That's our electronic eye. Then you've got its sensing face, the part that actually sees. And finally, we have the target, which is often called a dog. That's the thing the sensor needs to detect. And here's a crucial detail. The dog approaches the sensor from the side, laterally, as the turret rotates into position. Now let's look at the rule book, the manufacturer's own data. See, every sensor has rules for it to work reliably. And for this specific model, the FL2B-2J6, that rule is called the usable setting distance. Think of it as the guaranteed safe zone for detection, and it is a tiny, tiny window between 0 and 1.4 millimeters. So let's just lock that number in our heads for a second, 1.4 millimeters. That is the absolute maximum distance the manufacturer promises this sensor will reliably see its target. You go any further than that and you're officially in uncharted territory. All bets are off. And here it is. Here's our smoking gun. When we actually get the feeler gauge out and measure the gap between the sensor and the dog on this machine, what do we find? 1.5 millimeters. We are just 1/10 of a millimeter outside the specified range. It sounds like nothing, right? But in the world of sensors, that's a canyon. It's a massive problem. And this shot right here shows you exactly why that 1/10 of a millimeter matters so much. Because of that extra distance, the target dog is only covering a tiny little sliver, less than 25% of the sensor's active phase. The sensor is barely seeing the target. It's operating right on the ragged edge of its ability to detect anything at all. So this creates two major problems. When the turret is just sitting still, the signal is already incredibly weak. It's unreliable. But then, when the turret is indexing or rotating, that sideways approach of the dog makes that weak signal flicker and become even more unstable. The whole system is just fundamentally fragile. So we have an unstable setup. I think that's pretty clear. But that still doesn't quite explain why the alarm sometimes triggers when the turret is perfectly still. To get that, we need to talk about what happens when a sensor is pushed to its absolute breaking point. I want you to think of it like this. The entire system is balanced on a knife's edge. It doesn't take some big push to knock it over. Really, the slightest breeze will do it. And that is the core idea behind a marginal state failure. Because of that poor coverage and the excessive gap, our sensor isn't in a clear on state or a clear off state. It's trapped in this gray area in between, in what engineers call a marginal state. It's just flickering, waiting for the tiniest external nudge to push it one way or the other. And where do those nudges come from? Well, they come from the normal, everyday operating environment of the machine. These aren't other faults or big problems. They're just perfectly normal variables that a healthy, stable system would completely ignore, but that a marginal system just cannot handle. So what are these triggers? It comes down to three main things. First, just normal temperature swings in the factory. The datasheet for the sensor even says that can change the sensing distance by up to 10%. Second, tiny little variations in the machine's supply voltage. And third, and this is a wild one, even imperceptible vibrations from other equipment nearby can cause microscopic changes in that 1.5 millimeter gap, pushing the dog in and out of that marginal zone. So here it is, the complete anatomy of our so-called random failure. You start with insufficient sensor coverage. You add that suboptimal sideways approach of the dog, and then you just wait. You wait for a minor, inevitable trigger from the environment to come along and push it over the edge. And the result? An intermittent system fault. See, it was never random. It was predictable.
Okay, so now that we've totally diagnosed the disease, the cure becomes incredibly clear. And you know what? It's really simple. We don't need a new fancy sensor or some complex reprogramming. We just need to fix the fundamentals of the physical installation.
Take a look. On the left, you see the problem. The sensor is mounted over the bracket, which creates that critical 1.5 millimeter gap. And the solution? On the right, we simply remount the sensor under the bracket. That's it. This one small change moves the sensor closer to the dog and completely changes the physics of the entire interaction. And just look at the difference this makes. We go from a dangerously low 25% sensor face coverage all the way up to a perfect, solid 100% coverage. We're no longer teetering on the edge of detection. We are right in the center of the sweet spot. So this lays out the simple path to stability. By changing the melting from over to under, we get full coverage. That brings the gap well within that critical 0 to 1.4 millimeter usable range. And what that does is guarantee a strong, reliable signal that isn't going to be bothered by those minor environmental triggers anymore. Problem solved. So the big takeaway is this. Those random intermittent failures, they're almost never truly random. They are the predictable, logical outcome of an unstable system, a system on a knife's edge, just waiting for a little nudge. The real key is to find and stabilize that underlying instability.
And that really leaves us with a final thought, doesn't it? The next time you're faced with a random failure, instead of immediately looking for some complex cause, where could you look for a fundamental issue instead? A small misalignment, a marginal state, something simple that just might be the real root cause of it all.